Sorry, just 1 second. One of those weirdos that doesn't use a Mac. What'd you say? Ubuntu. All right, we're getting somewhere. Yeah, we're getting there. Okay, thanks everyone for coming, or thanks for staying. My name is Randy Zwitch. I work at a company called OmniSci. And this doesn't work. All right, there we go. And if you're, so again, my name is Randy Zwitch. I work at a company called OmniSci. I'm Senior Director of Developer Relations there. If you're not familiar with developer relations, my job is actually to come to conferences and give talks, which is pretty much the best job in the world, assuming you like public speaking, of course. But really, the purpose of developer relations is to work with users in the community to understand what you're trying to do, both in general analytics, but also how OmniSci might fit in with that. And then by having these conversations, working with the open source community, we can help inform how we prioritize features in the product. And so to give you just a little bit of background about what OmniSci is a GPU accelerated relational database. It was built from the ground up to run on GPUs. If you saw the keynote talk that was just 90 minutes ago, okay, the history of GPU computing was covered there. I'm going to briefly do that as well here, not from the same technical perspective, but I'm going to go over why you'd actually want to use GPUs for analytics. So every once in a while, when I have a talk to give like this, passion and work gets to overline, or they align, excuse me. And so what I'm going to do today, like I said, is show you OmniSci briefly, talk about why you'd want to use GPUs for analytics, talk about the Julia client that I wrote for OmniSci, and then talk about some future work and potential collaborations that I'd love to hear from the community if people are interested in. Okay, so why use GPUs? Okay, so charts like these are fairly frequent in any sort of, for lack of a better word, thought leader type presentations, right? Where data growth has now far outpaced the growth in transistors and clock speed in CPUs. And so this isn't really meant to be to scale. But at some point in the past, we hit the inflection point where data started growing faster than CPUs were able to keep up. And within the Julia community, really don't have to go into Moore's law too much. But again, as you try and add more transistors, eventually you need more power, eventually you generate too much heat, and it's not really a good way to increase performance. More efficient languages like Julia certainly helps, and multi-threading can help as well. But eventually you have a limit, theoretically on how much one CPU can do. Okay, so what did people start doing? Well, in the 2010-ish range, you started to see Hadoop become a platform that people were doing computation on. Rather than limiting themselves to one node, they started moving computations to multiple nodes of computers being synced up by kind of a head node or a couple of nodes. And while this is a way to approach the problem, it's not necessarily a fast way to approach the problem. So what you're doing when you trade moving all of your computation to a distributed system like Hadoop, unfortunately what you're doing is now creating an I/O problem where you're passing data back and forth between nodes. Very rarely do people just want to apply one function and just leave the data where it sits. Ultimately, you want some sort of reduction in data usually, and that's where sort of map reduce comes in. Map, you apply a function, reduce, you take some smaller sample, whether that's doing addition or filtering or whatever you're doing. And so that's how people originally started to solve these really large-scale problems. But again, you add the ability to have more cores, you're now creating an I/O problem. And so that itself, led to another sort of interesting, discovery. And so as Arch mentioned in his keynote, in the mid-2000s, researchers started to realize that GPUs or video cards were essentially just doing math problems. Okay, if you think about just your regular standard picture from a digital camera, whatever the resolution is, 5,000 by 3,000, that's a 5,000 by 3,000 matrix of pixels. Okay, those pixels represent numbers. Okay, and so people realized, okay, well, if we can use graphics cards to manipulate two-dimensional arrays of pixels, why can't we just use them to do two-dimensional matrices? Okay, people started in science and engineering started to use video cards. NVIDIA then came out with CUDA, which really helped out in terms of providing an API for talking with video cards at a slightly higher level. If any of you have ever tried to write CUDA, it's not really high level. It is slightly higher level though. And so what GPUs provide over CPUs is the fact that you can have 500 or 1,000 times more cores, right? Your desktop maybe has 8 cores in it. Even a high-end consumer GPU at this point approaches 4,000 or 5,000 cores in it. And so you maybe say, well, why don't you just have more cores in CPU? Well, we just talked about that, right? GPUs are fundamentally a different architecture. And the way I like to think of this in layman's terms is the difference between a bus and a Ferrari. So if you need to move one person around a racetrack as fast as possible, okay, you're going to choose a Ferrari. But if you need to move 50 people around the same racetrack, the bus will actually get there faster by driving slower, right? Because it's going to take one pass around the track, but it's going to take 50 people with it. And so this is really exploiting throughput of calculations, not the raw speed of an individual calculation. And again, as you can see, at some point in 2008, 2010, CPUs sort of leveled off. GPUs are still growing. I don't know if it's necessarily exponentially, but you are seeing massive performance increases between each new architecture that comes out. And so with this rise of GPUs, OmniSci, the company, was born. Okay. Separated at birth. Okay. This is somewhat facetious, but somewhat true maybe. Julia predates MapD. So originally, we rebranded. So you may have heard of a company called MapD. We became OmniSci last fall. And Julia predates MapD by a few years. But what's interesting to note is the similarity in timelines of the Julia project and MapD, which became OmniSci, especially once LLVM was in the picture. And so in this timeline here, our founder, Todd Mostak, was at Harvard at 2011 to 2012. He was doing work at the Center for Middle Eastern Studies, and he wanted to use Twitter data to get the sentiment of users in the Middle East during the Arab Spring. And so as he started doing this more and more and more, it started to become a computation problem, not just a sociological problem. And so from his research, he actually started doing this on GPUs because it took too long to process the data, and that's where MapD was born. And so in 2013, our founder ended up going to MIT CSAIL, was working under Sam Madden and Mike Stonebreaker to actually turn this into an actual database. At that point, the company was founded. It moved to GitHub in 2014, and then May of 2017, MapD core was open sourced under the Apache 2.0 license. And so while I was being somewhat facetious, if you don't look too hard, there's a lot of similarities in this story from the geographic region of the US, the rough timeline, and some of the technology that underlines both OmniSci and Julia. It's interesting also to note, so I started using Julia before I started working at OmniSci. And when new users come in with Julia, there's always did you pre-compile it before you timed it? That absolutely happens with OmniSci too. And it's like, you go talk to these different places and it's like, oh, well, the first runtime's really slow. Yeah, I know, because it's being pre-compiled. And so, it's really funny, at least been funny to me, how similar that experience has been. Okay. Actually, before I move on, so in the upper left hand here, this was actually the original research. It was just creating a map showing the level of Islamicist sentiment in the Middle East. And this became really the original demo of MapD. Of course, after quite a few years and a huge injection of venture capital, a lot of engineers and employees, we've done better. And so if you were familiar with MapD or OmniSci before this talk, you've probably seen this demo. So tweet map demo, something like 1% of tweets are available publicly from the Twitter API, and of that, 2% of them are geocoded. And so we save that every day. That ends up being around, I think, 1 million tweets per day that we stream into this demo. And so if you actually wanted to go through and see something that's happening in pseudo real time, like an earthquake or something else, you could actually go to this map, zoom in, and start to see what people are talking about. Of course, we have a little bit of a delay, and however, the Twitter API delays as well. And so it's not exactly real time, but it's pretty close. And like I said, if you were familiar with OmniSci before this talk, you've probably seen someone like me do this demo. But since it's been a few years since we did this is actually not as impressive anymore. As GPUs have gotten better and better, we've kind of done bigger and bigger things. And so rather than go to the cruise last night, I actually stayed and tried to build a bigger demo than this. So we're going to try it out here. Could go completely off the rails. It actually uses functionality that's not part of our current product set, and so we'll just see what happens. You can't really see that, can we? Can we turn the lights on? Sure. Not better. That's a little better. So what I did last night was take all of OpenStreetMap, the entire globe, and try and import it into OmniSci. And so what you're seeing here is actually that result. Of course, up to this point, I've been talking about using GPUs for computation. Of course, GPUs are used for graphics. And so we use GPUs for both of these, both computation and graphics. And so if you want to do large-scale visualization, you can't stream the data back to your browser, right? D3 and all those related JavaScript libraries are amazing if you stream 1,000 points back to the browser. If you try and send 120 million or 1 billion points back to your browser, you're going to crash the local computer. It's going to take so long, you're not really going to have interactivity. And so I can't really see. There you go. Okay. So this is all of OpenStreetMap for Baltimore. Okay. Now the thing about GPUs, or the thing about OmniSci, is we very much have the same ethos as the greedy quote he mentions. Okay? We don't want to just sort of do things, right? Anybody can render this map. You will see things like this on the local news. Okay? They do pre-render their maps. Okay? But if you want to do actual analytics and play with your data and interact, okay, you can't pre-render. And so there are no indexes. I can type in any value here and instantly render the map. And so I'm going to try and guess here. Somebody yell out something. Some country, some anywhere. Leeds. Okay. So it's clear, I mean, I guess I could be working with whoever shouted out Leeds. Okay. Nobody expects Leeds. I'm sorry? Singapore. Singapore? The hardest thing is actually getting my mouse in the box over here. Nope. Missed?
You kept Leeds.
Okay. And of course, it's not enough just to look at something. Why not look at it really close? Okay. So I don't want to belabor the point here, right? You can pick any location. All this data is instantly available, rendered, sent across as a PNG, and you get actually the same level of frame rates that you would get from video games. Because again, GPUs started out rendering graphics. Now what's interesting about this, and the fact that there's no indexes, is actually because it's really slow to calculate an index, okay? If you're used to regular databases, you insert your records, and you try and build an index that people are going to use in the future. Well, if you're lucky, people actually write a query where they hit the index. If they write a query where they don't hit the index, you're going to have a bad time. All right. Okay. In the case of OmniSci, we don't even support indexes, okay, because indexes are slow. And what this implies is, as soon as you can stream the data into the database, you can interact with it in a dashboard. Okay. Here, I loaded all of the OpenStreetMap data in at once. We have another demo that reads bike share data right off the bike share API, bike share APIs. It's called the Greater Bike Share Specification. And so that data actually streams right in, and you can just go through and actually see the actual location down to 1 minute where every bike is in the world that is part of that specification. Okay. So this starts to show you the power of using GPUs for analytics. You can use them for rendering, really large group by queries. So much of analytics is actually some sort of reduction operation. And so when we're talking about billions and billions of records, okay, a human can't look at a billion's worth of records, right? So you're going to write your query. Okay, OmniSci supports standard SQL. So you write your SQL query, you generate some result, and we return it back to you in many cases less than 100 milliseconds. But now I'm going to be the buzzkill. This is Enterprise Edition. Okay? This is not open source. As you can imagine, it takes quite a few engineers to be able to pull this off, to be able to overlay graphics on top of geospatial charts. Okay? Oop. Lost my... So this is my actual unveil. So OmniSci.jl. So as I talked before, occasionally you get lucky where passion overlaps with work, and this is one of them. So I started at OmniSci around 18 months ago, and just as sort of a goof, I thought like, oh, well, what if there was a Julia client? There was already a Python client. I actually maintain that as well. OmniSci uses the Apache Thrift project, which is a serialization library so that you can send messages back and forth. And so any message that conforms to the Thrift specification, it doesn't matter the language. You just send the message and it returns a message. And so I was lucky. Tanmay actually wrote a Thrift compiler for Julia. And so without his work specifically, this wouldn't even exist. And of course, there's lots of other libraries that people have written that end up being really important for this library. And so one of the great things about this is, okay, not everything is a pretty picture, right? Some people actually do calculations for work, okay? So you can write your query, and this will return a data frame. And what's great about Julia and the richness of the type system is I've set this up in such a way that when you query the database, it returns the exact types. And so you rarely see this with databases because it's very difficult to represent things like geospatial types, or arrays are a little easier. But in this case, if you pass an array, a geospatial type for upload, it will go into OmniSci. It will be uploaded geospatial. You can do massive geospatial calculations on the GPU. You can return them back as a data frame. Same thing if your data is already on OmniSci and you want to bring it locally to Julia, it will create all of the types locally, geospatial, so points, lines, polygons, multi-polygons, and things of that nature. Okay. This is open source. Okay. Again, this is one of those things that I find, at least, or I think, is a foundational element to the database. More so because of what it implies. Okay. With the opportunity of passing your calculations to a GPU-enabled server and returning the results back in milliseconds, okay, I think it can open up a lot of interesting avenues of collaboration. So first, the two-language problem. So I just mentioned I'm also the maintainer of our Python library. It's fine. There's nothing wrong with Python. But we have started trying to implement runtime user-defined functions. Okay? And you can imagine if we have Python over here and we have OmniSci over here that's expecting LLVM, it doesn't quite work, right? You can't pass Python code and just hope things happen. And so what we do is we use Numba, which is a compiler project for Python, to generate LLVM IR, intermediate representation. Okay. Does anyone know of a language that can do that? Okay. Julia, right? And so I think this is possibly the thing that I'm most excited about. I don't know how to do it yet. I can certainly work on it at work. But using Julia and or CUDA native to just pass any arbitrary Julia kernel to OmniSci and run it inside of a gigantic GPU-enabled database, to me, I think is going to be groundbreaking. Julia is fast on the CPU, but passing it to something that has 25,000 more cores is going to be a lot faster. Okay? And with that, there's, I think, another opportunity. So the data frames library in Julia, it's getting very close to being the 1.0 magic release. But we don't have anything for a GPU data frame. Okay? And I think that hampers the ability of many sort of non-science workers to actually move towards doing GPU computing. There's already an industry effort called RAPIDS that was led by NVIDIA. It was originally called the GPU Open Analytics Initiative by a number of companies, including MapD and OmniSci. It all sort of rolled together under NVIDIA. They provided engineering support. They have a library called cuDF, so CUDA data frame. It first started out for Python, mostly written in C++. They just announced Java bindings for it. And so the question is what is the opportunity here? It'd be cool to have it in Julia regardless. An array of named tuples might be enough. I don't know. Or creating a Rapids compatible one to plug into all these other projects out there. And so again, this is an open question. I would love to talk to anyone who's interested in this about collaborating because I think having a GPU data frame library would be very interesting. Apache Arrow. If you were in the Birds of a Feather session yesterday with databases, we actually talked about this. This is somewhat in progress. And then lastly, Mach-E, right? So Mach-E uses WebGL in some places. What if you could pass a GPU buffer directly to Mach-E, right? So now you have Julia, you're leaving your result on the GPU, you're rendering and sending back a picture. That's how the OmniSci rendering engine works. You do your computation, leave it there, and send back a picture. What if we did that on Mach-E? What if there's things that I don't even recognize, right? I'd love to talk to anyone who's interested in doing GPU-based analytics, anyone who's already using NVIDIA GPUs to accelerate whatever it is you're accelerating. I'd love to talk to you about it. And with that, that's my presentation. I'm happy for questions. If there's no questions, I bought a bunch of free stuff. I have T-shirts, canvas bags, webcam covers. I might have pens. I probably have stickers. Please take some of them, or please take all of them. The Developer Relations Walk of Shame is bringing back free stuff back to your house. If I bring it back home, a new box will actually show up. So please feel free to take as many things as you'd like. So thank you. I don't want a question from Jeff.
Hi, cool stuff. Could you tell us what the specs of the hardware were behind the demo you were showing?
Sure. So the demo I was using was a Microsoft Azure ND24 instance. So it had 4 P40 NVIDIA cards, which is 96 GPUs, approximately 16,000 cores.
What does that cost per hour?
For a long time, it was free for us. It's something like $6,000 a month.
Not too bad. Yeah. All right, thanks.
If you actually end up using OmniSci, there's no Microsoft Azure people here, are there? AWS? All right. Buying your own hardware actually pays off very quickly. So we love partnering with clouds. We will run in the cloud. We will run in your own data center. We run on consumer-grade cards as well. NVIDIA doesn't really want us to say that so much. They want you to buy data center quality, but if you want to use the open source project on consumer hardware, it absolutely works. We provide Docker images, binary downloads. You can compile from GitHub. Basically, any NVIDIA GPU works.
Hi. Cool
Recent
stuff.
GPU.
Yeah, cool stuff, first of all. Thank you. Can I run it on CPU for some time until I have a GPU to test it later?
Yes. So while OmniSci was built to run on GPUs, we will run in CPU mode just because there are some operations that aren't easily parallelizable, and so we'll punt to there. We also do, I don't know if it has a real name, but sort of intelligent caching. And so the reason why OmniSci can be so fast is once the data is on the GPU, okay, now you're just working on in memory. If your data doesn't fit in the GPU, we fall back to CPU RAM. If it doesn't fit into CPU RAM, then we just read it from disk, and of course that's going to be as slow as the hard disk is. And so yes, you can actually run this. If you wanted to play around with OmniSci in general, We have CPU-based Docker containers, binaries, the whole thing.
What is the difference between the open source and the enterprise version, if you can summarize it quickly?
The quick part is that the open source version does not have enterprise features. It doesn't support single sign. Sorry, I'm feeling a little trolly. It doesn't support single sign-on. We provide the ability to run in distributed mode through that. ODBC is part of our enterprise edition. So various enterprise features. There's no limit or restriction on the open source side. So as many cards fits into whatever hardware you have, you can use. And so generally 8 cards is the maximum in a server. So you could run on 8 GPUs if you have them.
So the distributed is multiple.
Distributed is multiple nodes. So
Okay.
OmniSci open source works on as many cards in one node, and then distributed is multiple nodes. That is fairly uncommon. If anyone here thinks they need that, though, please come talk to me.
So if you're not indexed, is every query a full table scan?
Yes and no. So yes, in the sense that there's no index. Okay. With this caching that we have, okay, we're bringing in the data into GPU RAM, and so it's going to sit there as long as it's being used. And so in the same way that Julia precompiles one query and then you run it lots and lots of times, that visualization I was showing you, the only thing that was changing there was the bounding box. Okay, that was the same exact query every single time. When I typed in Sri Lanka or what did we do, Singapore? We did Leeds, right, where, where a location equals Leeds, where a location equals Singapore. Okay, and so the answer to that is yes, it's a full table scan, but if that fragment's already in memory, then it's very fast. You're doing it in parallel.
Is the OmniSci database a persistent store, or is it just a SQL?
Yes, it's a persistent store. So right now, we store in a specific our own format to quickly serialize some or deserialize some disk. We are working on a foreign storage interface, and our first target is Parquet.
How large, how much data can we put in one of those databases?
There's no practical limit. It comes down to how much data you have, or how much hardware you have. And we are a columnar database, and so you can literally do the calculation of, I have a 64-bit int, and I have 320 gigabytes of RAM. That'll be your limitation.
It's a RAM limitation, not a disk limitation?
Yeah, it's not really a disk. I mean, it's limited how much disk space you have too, right? I mean, but there's no practical limit like 2 to the 64 or some records. It's many. All right, thank you everybody for listening.